Now moving towards the robust tracking and disturbance rejection problem. So far we had the complete knowledge of the ABC parameters. So first of all, if we recall the state equation, Ax plus Bu and y is equal to Cx. So if we have the complete knowledge of these parameters ABC, then we say that we know very precisely the information about the plant. Now if there are some changes in the practical plant, then whatever modeling you have done to extract this ABC won't be equal to the nominal values, and these changes could happen because of the change of load or the environmental condition or aging of some electromechanical components. So the plant parameter variations often occur in practice in terms of A, B and C. Now the equation used in the design, whatever the equation we have used, we call it the nominal equation by taking this ABC parameter. Now if we recall the tracking problem, the design of the computation of the feed forward gain P depends entirely on the plant parameters, that is beta 4 and alpha 4 bar. Now if those are not the actual parameters of the actual plant, then computing that P for from the nominal equation won't result GF is equal to 1. So in that case, you won't be able to have the tracking for any reference input. So now even if we design P in such a way that if there are some deviation of the plant parameters or some disturbances, if we are still able to achieve the tracking, then it would call the non-robust design or the robust design, sorry. Okay. So we now will discuss a different control design technique that can achieve robust tracking and disturbance rejection. So this topic of robust tracking and disturbance rejection is a very wide topic, and here we would see a glimpse of how of designing a controller for a basic problem to illustrate the idea. So consider a plant. So first of all we'll see how the control problem looks like. Consider a plant described by a linear time invariant system affected by a constant disturbance W with unknown magnitude, which enters at the plant input. Now if this input is entered at the plant input, so then in that case the state equation is given by x dot is equal to Ax plus Bu plus Bw. The distribution matrix of the disturbance signal would also remain the same. Okay, and y is equal to Cx, and we denote this equation as disturbed LTI because of this W signal. The problem is to design an overall system or the closed loop system so that the output y of t will track asymptotically any step reference input even with the presence of disturbance Wt and with the plant parameter variations. Okay? So this is the system we have considered so far without the inclusion of the disturbance signal. So we can expect that if we have not taken any significance of this signal onto the response, then we won't be able to achieve the desired objective either in terms of the desired rate or the regulation or the tracking. Okay, so we need to solve this problem where we have this W which is unknown or of unknown magnitude, so that we are still able to achieve the tracking on the regulation. Okay, so in order to solve this problem, in addition to introducing the state feedback, we will introduce an integrator and a unity feedback from the output. So let's see how the setup looks like. So if you are not able to see this line, this here is a line. Okay, so let's pay attention to here for a couple of minutes to see how what loops are being considered here. So this is the plant, the LTI system. Now when we include this W as we had seen earlier, so we would have this disturb LTI by including this W also. Let's call it disturb. Okay. Now this part is the state feedback. This one is the state feedback controller. We have designed, or we have been designing so far, so that the eigenvalues of the closed loop system can be placed at a desired location, right? And it goes as it contributes to the U as kx. Now this is the reference signal which we want to track. Now in between this path we have introduced an integrator with again k. Now we have two design parameter once again. One is the k and another is ka. We would going to explore a bit this control structure to finally solve our problem. Okay, so let the output of the integrator be denoted by xa, an augmented state variable which would be given by, so if we see from here, x dot a is given by the difference of r minus y, and y is nothing but y is equal to cx. So if we recall our original plant, which was x dot is equal to ax plus bu plus bw, and if I augment this state and form a new vector, let's call it x tilde, and denote a new state vector as x and xa transpose. Okay, so in that case we would have x dot xa dot one from u, another from r, and another from w. So we need to see what would be the associated matrices and vector with respect to different variables u, r, and w. So if we see here, we would have b 0, b x dot a is defined in terms of x, it would be 0, 0 and 1 and 0. So this would be our augmented plant. Now we have these states. This could be written in terms of, let's say, x tilde dot is equal to a tilde x tilde plus b tilde u plus b matrix with respect to r plus b tilde b tilde and w. Okay, so this would be the overall plan for which we need to design a robust controller. After including this state, we got this state space system. Okay, now for this plant, we design the controller as u is equal to vector k and ka, taking the feedback from the augmented state, which is x tilde. So this we can say as k tilde, and this one as x tilde, which we have assigned. So our u would be given as k tilde and x tilde. Okay, now substituting this u into the augmented plant system, we would obtain this closed loop system, where we, by including this ka, we would get this overall augmented, disturbed, closed loop LTI system, where this K with the addition of this Kx would add into this. So if you recall the A tilde matrix, it was A 0 minus C 0. Okay, this was X tilde, and B we had B0 and U. Okay, now if I replace U from here to here and adding the associated terms, I would obtain this A matrix. This B matrix with respect to this reference signal would remain as it is. Similarly with respect to the disturbance signal, because R and W are the signals which you cannot control. You only have the control over the signal U, and the transformed C matrix is given by this. Okay, now first recall one of the results, so which would help us to further design the controller. So if the original AB pair is controllable, and if the transfer function of the plant has no zero at s is equal to 0 or at the origin, then all eigenvalues of the new A matrix, now this new A matrix is nothing but this one. Okay, the new A matrix is this one, which is the closed loop matrix, the state matrix, closed loop state matrix. New A matrix can be assigned arbitrarily by selecting a feedback gain Kk. So this is the very important result, which speaks about the designing of a state feedback controller, and depends on the controllability and also the non-availability of a 0 at the origin. Now there are many implications of this lemma. So if you recall one of the previous results, or one of the first results, we had said that if the AB pair is controllable, then with the application of the feedback controller, A minus Bk comma B would also be controllable. Now here we are speaking about the placement of the arbitrary placement of the eigenvalues of the new A matrix. Okay, by the selection of Ka, which is meaning to say that this and this pair is controllable, which is equivalent to saying that AB is controllable. So we will see that how we can do the proof of this one. So we show the theorem for n is equal to 4, again by taking a transfer function. So two assumptions we had taken here. So first of all, given any form of the original ABC pair, we have transformed into the controllable canonical form, so that the visualization becomes pretty much easy. Second, the transfer function has no zeros at s is equal to 0, and the condition we had seen earlier, and it is only possible if and only if the beta 4 is not equal to 0, considering the transfer function for n is equal to 4. Okay, so taking these assumptions forward, the proof rests that we now show that the pair, and this pair is nothing but your A tilde and B tilde, is controllable if and only if beta 4 is not equal to 0. If we are able to show this, then we have proved this lemma. Okay, so first of all, it should be clear that why if we show the controllability of this pair proves this lemma. Again, considering the fact that this closed loop state matrix is obtained for the augmented plant given by this one. So either we show the controllability of this and this pair, or the controllability of this and this pair, because the result says that if this pair is controllable, then this pair would definitely be controllable. So either we show the controllability of this one or the controllability of this one, which is equivalent to saying that we can place arbitrarily the eigenvalues. Okay, the another condition is that the origin, there should not be a 0 at the origin, which is equivalent to saying that beta 4 is not equal to 0. So if I combine all these statements, if we are able to show that the augmented pair A tilde B tilde is controllable under the condition that beta 4 is not equal to 0, then we have completed the proof. So let's see. So note that the dimension of this new pair is 5 because of xa. Since xa is a scalar, the dimension of this a would be n, but c is a vector, is a row vector, and since we have considered n is equal to 4, so the overall dimension of this state matrix would be 5. Okay, the controllability matrix of this new pair can be written as B. It would be A times B. This would be A square B, and A square B, note that we need the square of this matrix, or the with the multiplication of this B, and similarly go on for A cube B and A to the power 4B. Okay, so this matrix you can compute and verify by yourself by putting this new A matrix and this B matrix here. So computing this controllability matrix from the controllable canonical form of the original A matrix, where if you notice we now specified in terms of alpha i's and beta i's. Okay, this you can readily obtain if you substitute here A in the controllable canonical form. Okay, now we do two operations onto this controllability matrix, that the row 5, that is, this is row 5. Row 5 is now changed to row 5 plus beta times row 2. So if we multiply this complete row by beta and add this into R5, so this would be our first operation. The second operation is that we multiply the the fourth row by beta 3 and then again to the row 5. So doing these two elementary row operations, we obtain this controllability matrix. Now if you pay attention to this controllability matrix, that first of all it is an upper triangular matrix, and the determinant of this matrix is minus beta of 4, which meaning to say that the matrix is non-singular if and only if beta 4 is not equal to 0. So we have started to show the controllability of this matrix. We have written the controllability matrix, or we wanted to compute the rank of the controllability matrix, which should be a full rank, and it should not be a singular matrix, and it is possible if and only if beta 4 is not equal to 0, right? Which establishes the result. Okay, so now we'll discuss by taking that lemma or whatever the results we have obtained from this lemma. We will, over the next 5 slides, we will carry out the design of the robust controller. So consider again the augmented disturbed closed loop LTI system, where we have obtained this A, B, the rest of the matrix associated with the state, the reference signal, and the disturbance signal by substituting the control law. Okay, the control law, if you recall, is given by U, K and K, X and X. Okay. So assume that a set of n plus 1 desired stable eigenvalues has been selected, and the feedback gain Kk has been found such that we are able to write the characteristic polynomial of the closed loop system. So A is of n-dimensional, C is a row vector, so the overall dimension of this closed loop system would be n plus 1 cross n plus 1. Okay, so for example, we have computed that where we need to place the desired eigenvalues, and that would be n plus 1 eigenvalues. Now using the state feedback, we can also compute the characteristic polynomial of the closed loop, which is nothing but Si minus this matrix, and I matrix would be of n plus 1 dimension. Okay. Now we show that the output Y will track asymptotically and robustly any step reference input RT is equal to A and reject any step disturbance with unknown magnitude. Okay, so now we'll start to solve the problem by using that control structure. So first of all, we will recall that control structure once again. Uh, this part is the original LTI part. Okay, and just and between the reference and the U, we have added an integrator with a constant gain K. Now, if we pay attention to this block, and I write the equation, I can write U bar as U plus W, and U is nothing but V plus K times X. So U bar is nothing but V plus Kx plus W, where V plus Kx is U. Now, after rearranging the term, I can write V plus W as V bar by taking Kx separately and assigning V plus W as V bar. Okay, so this is just a simple algebraic manipulation because the output signal U bar has not changed. Okay, so this complete box I can replace by this box where still the output of this box is U bar. Okay, which is now taking the feedback Kx. So U bar, if you see from here and here, U bar is Kx plus V bar, and V bar is nothing but V plus W. Okay, so this small block I have replaced with this block. Now the next step is to compute the transfer function from V bar to Y. Okay, so V bar to Y, it's nothing. So if you see V bar to Y, we already have the state feedback here, and this would be equal to the nominal case of the state feedback with the inclusion of this A minus BK into the A matrix. Okay, and we assign it N bar over D bar, where D bar is the determinant of this matrix. Okay, now see the rest of the part. So this should be G bar in fact, G bar hat, because G bar hat is now this complete part with the state feedback. We have replaced this one. The okay, let's write it clearly so that the things would become clear. This is V bar hat and Y hat S. Okay, so the transfer function between excuse me, it should be opposite. That the output is Y hat of S and the input is V bar hat of S in the frequency domain. Okay, so we have replaced from here to this small block G bar hat, whose input is V bar and the output is Y. The rest of the part remain as it is. We combine this K by S, whose output is V now, and the inclusion of this W and this output. Okay, so this overall block diagram, can be simplified to this one. Okay, where G bar hat already includes the state feedback K, the feedback from the X. Okay, now let's move further. So if I pre-multiply this matrix, which is the Si minus A matrix of the augmented disturbed closed loop LTI system, if I multiply it by any unimodular matrix, so by taking into account the property of the matrix, it won't change anything. So I can write as equal to this one, where the unimodular matrix has been chosen as this one. Okay. Now taking the determinant both sides, the determinant of a unimodular matrix would be 1. The determinant of this one would be this polynomial delta, which is the characteristic polynomial of the feedback, closed loop feedback. Now this one, since this is again upper triangular matrix, I can write it as the determinant of this one times the determinant of this one. If you see that the determinant of this one is nothing but D bar hat from here. D bar S is the determinant, is equal to determinant of this one. Okay. the determinant of this one would be s plus, if you pay attention to this part, this is nothing but this g bar head transfer function, this g bar head transfer function. Okay, which is n bar by d bar times ka. So I can simplify this term as s times d bar s plus ka times n bar s, right? So this is the key equation here, which we will going to use it further. So we know this delta f would become equal to s d bar s plus k n bar s. Now again going back to the entire closed loop system, again this is g bar hat. So first of all, let's see the transfer function from w to y. Okay, let's see first this part. This we can write the forward transfer function, which is n bar over d bar, and the closed loop polynomial, which is 1 plus ka times s into n bar by d bar. Okay, now simplifying this one would yield s into n bar divided by the characteristic polynomial of the closed loop feedback system, which is natural. Now assume if the disturbance is some constant signal w bar for all t greater than equal to 0, whose magnitude is not known to us, then we can write w bar as w hat as w bar by s in the Laplace domain, and the corresponding output y hat w would become s n bar by delta f into w bar by s. So you would see that this s has been cancelled naturally, and the response y for the given w is now given by w bar n bar divided by delta f. Now if this delta f is a stable system, then the response from w would always go towards to 0 as t tends to infinity. Okay, now if there are plant parameter variations and also variations in the feed forward gain k and the feedback gain k, the rejection still holds as long as the overall system remains stable, because the responses with respect to those signals would always die out as t tends to infinity. Okay, so this is important thing here, that although we do not have any information about the signal w, but still the output of the closed loop system is not at all affected by the presence of w as t tends to infinity. Okay, now see the tracking thing. Let's see again the transfer function from r to y denoted by g hat yr. Now this transfer function would be denoted by k by s, the forward part transfer function, plus the denominator part represented by 1 plus k by s n bar by d bar. Again simplifying this thing, we get k times n bar divided by the characteristic polynomial of the closed loop system. Now we see that if I compute the DC gain of this transfer function, I would have ka times n bar 0 divided by delta f has been already expressed as s times d bar s of s plus ka times n bar of s. Substituting s is equal to 0, this part would go away and we would get g hat yr, the DC gain of this transfer function, equal to 1, which was the objective of the tracking, that the transfer function or the DC gain of the transfer function from r to y should be equal to 1. Yeah? So the above equation holds even when there are plant perturbations in the plant transfer functions and the gains, because we had seen earlier already that the response affected by those disturbances or the variations would die out, and thus the asymptotic tracking of any step reference input is robust. Note that this robust tracking holds even for large parameter perturbations as long as the overall system remains stable. But there are some design considerations also, which we will talk about a bit later. But the key observation here is that one thing you have noticed, that we have included an integrator into the design of the controller, and this integrator is in fact nothing but the model of the disturbance, because the disturbance was taken as a constant signal and the Laplace transform would be an integrator. So we have included or implicitly we have included a model of the step reference input and the constant disturbance. So this way of designing the controller is also called the internal model principle. We could also see the stabilization problem next. So far we had discussed whether if the plant is controllable, then the eigenvalues could be arbitrarily assigned. But the problem here that we want to design a stabilizing controller whenever the state equation is not completely state controllable. So here we would recall some of the concepts of the stabilizability, which requires the decomposition of the original LTI system. So from where we could extract the uncontrollable state equation and also the controllable state equations. So by doing this decomposition, we know that the pair AC bar and BC bar is controllable, and this is the homogeneous part which is uncontrollable. Okay. So now, because the new A matrix, this is the new A matrix after the decomposition, it's just a new A matrix in the sense of representation. This new A matrix is block triangular. The eigenvalues of the original A matrix are basically the union of the eigenvalues of AC bar and AU bar. This thing you can also prove by yourself. The implication of the statement is that you can compute separately the eigenvalues of this AC bar matrix and separately the of this matrix A bar U, because both these matrices would be the square matrix. Now the overall eigenvalues of the original A matrix would contain all the eigenvalues of A bar C and AU. Okay. So now let's see if we introduce the state feedback controller, which we have been designing from the beginning, to this system which is not completely state controllable. What happens to the closed loop system? So we can write U is equal to R minus Kx. Now since the X has been changed to X bar by using the decomposition, so we have replaced as K bar, and we now need to design this K1 bar and K2 bar with respect to XC bar and XU bar. XC is the controllable state and XU is the uncontrollable state. Okay. After applying this U to this controllable decomposition, we obtain this closed loop system where these K1 and K2 are been only added to the first row or block row of this decomposition. So here we see that the matrix A bar U and consequently its eigenvalues are not at all affected by the state feedback. We are only able to affect the eigenvalues of the controllable part. Okay. Thus we conclude that the controllability condition of AB is not only sufficient. So this we had stated earlier on the slide number 13 in terms of only the sufficient, but in fact it is also necessary to assign all the eigenvalues to any desired positions. So if AU bar matrix is stable and if AC bar BC bar pair is controllable, then the state equation is said to be stabilizable, which is the definition of the stabilizability. So now if so these three comments are important because the tracking and the rejection problem we have discussed so far when the pair is completely state controllable, but if it is not completely state controllable, we could use this weaker condition of stabilizability to show the previous results for the tracking and regulation problem. But we need to take care of two main things, that when the system is controllable, we have the complete control over placing the eigenvalues. But with this weaker condition, we do not have the complete control on the rate of tracking and rejection, okay, which is basically linked to the placing of eigenvalues. Now, so suppose if the eigenvalues of the uncontrollable part is stable and they have large imaginary parts or are close to the imaginary axis, then the tracking and rejection may also not be satisfactory. Okay, so these two points should be noted while addressing the tracking and rejection problems for the systems which are not completely state controllable but stabilizable.